Hey everyone, welcome back to another video by Camroom 5. In today's set of videos, we're going to start with a new concept of transition element chemistry. We're going to begin with the first row of these transition elements, and we'll see the atomic structure of these elements first. Just outside the nucleus, we have the 1s subshell, which can hold 2 electrons in it. Just outside the 1s subshell, we have 2s subshell and 2p subshell. 2p subshell we know has 3 orbitals px, py, pz. Then we can see 3s subshell, which is spherical, and then 3p subshell with again 3 orbitals. But before we can expect the 3d with all its 5 orbitals, we have 4s2, because 4s has slightly lower energy than the orbitals of 3d, and then obviously 4p comes after 3d. Let's recall that 2s and 2p, which is the second energy level, are together. Just outside the second energy level, we have 3s and 3p together, but 3d has 5 orbitals which have higher energy than 4s. So 4s comes first, before 3d, and then 4p continues after 3d. Using these understandings, we should be able to write the electronic configuration later. Let's write that the energy level of 4s is very slightly lower than the energy level of 3d. So let's recall our understanding and let's have a practice of writing electronic configuration of d block elements. First row only, by the way. We begin with scandium, which is the very first element in the d block series. It goes till the end where atomic number 30 zinc shows up. The atomic number begins at 21 from scandium till 30. The standard electronic configuration 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2 comes first, then 3d1 because there's 1 electron in 3d. All these elements have very similar configuration where the increment is 1 electron each. You can find something interesting with chromium because 3d4 means that it's almost completely half filled. So 4s gives away 1 electron and then 3d becomes 3d5. So 4s1 and 3d5 can be expected in chromium because 3d5 is more stable. Then after chromium, things continue to add up till copper, where you can see again that 3d9 means it's very close to completely fulfilled. So 4s again gives away 1 electron towards 3d and 3d becomes 3d10 because completely half-filled and completely fulfilled stable. You can also notice that from 1s2 till 3p6, it represents the electronic configuration of atomic number 18, which is a noble gas configuration for the noble gas argon. So it is okay to write these configurations in a simpler way with square bracket argon and then the configuration. Let's write our 2 important takeaways so far. Electrons of these atoms, let's put this in inverted commas, electrons of these atoms in isolated gaseous atoms are present in d orbitals. Why did I write isolated gaseous atoms? Because I don't mean ions, I mean atoms which are not bonded. And then when we talk about chromium and copper, we talked about it already. Chromium and copper allow the excitement of 1 electron from 4s subshell, or you can say 4s orbital, to the 3d subshell. 3d subshell has 5 orbitals, by the way. That is something we'll talk about also. This allows the d orbitals to be completely half-filled or full-filled. Half-filled in the case of chromium and full-filled in the case of copper, because 3d5 and 3d10 offer higher stability. So for additional stability, this happens. I hope we are clear so far. Now, We will talk about the electronic configuration of the stable ions of D block elements. We will pick some examples and we'll see how it works. For instance, if you were to talk about the most common ion of scandium, which is scandium plus 3 ion, the configuration becomes 4s0 3d0. There's literally no electron in the 3d subshell. In a very similar way, other elements also like tellurium plus 2, argon, and then 4s0 3d2. When we talk about vanadium with, like, for example, plus 3 ion, for example, it can make multiple. So we get argon and then we get 2 electrons lost from 4s, so 4s becomes 0 and then 3d2. Similarly, chromium makes plus 3 ions, so chromium, argon, and then we get 2 electrons lost from 4s. I know one was excited and then it becomes 3d3. At the end of the day, we know that always the electrons from 4s are going first. Manganese also loses 2 electrons from 4s and then becomes 3d5. Iron does a similar work, so it becomes 4s0 3d6. Cobalt, nickel also make plus 2 ions. So again, 2 electrons are always going to lose from the 4s subshell. Similarly, for copper, the same thing happens where copper becomes 4s0 3d9. You can see that right here, 4s0 3d9. Zinc, after losing 2 electrons, become 4s0 3d10. 2 of these elements are never considered transition, and that includes scandium and zinc. Why do we not consider them as transition elements? The reason is that by definition, transition metals, now you need to write this definition by the way, transition metals have one or more stable oxidation states. So this is the first part of the definition, where transition metals have one or more stable oxidation states with partially filled d orbitals. It's about the stable oxidation state having partially filled d orbitals. Scandium has no electrons in 3d and zinc has a complete electron in dd. When we talk about an important property of transition elements, it is their variable oxidation state. To explain that, I'm going to compare transition element with a typical group 1 and group 2 sodium and magnesium. You can see their ionization energy values keep on increasing. For example, for sodium, there's a big jump after the first ionization energy. From 494, it becomes 4560. Let's talk about the reasoning, and then we will compare it with transition. So for sodium, the last electron, outermost electron, is in the 3s subshell, which is lost in the first ionization step. If you want to lose the second electron, it has to go away from the 2p subshell, and that is why there's a big difference, because 3s has a very high energy than 2p, and there's a big difference between the energies of 3s and 2p. So after the first electron is lost, it's not easy to lose the second electron because of the big energy difference between 3s and 2p. For magnesium, you can see there's a big jump after the second ionization. Why is that? So let's recall the electronic configuration of magnesium. As I write the electronic configuration of magnesium, you can notice that the last 2 electrons are in the 3s subshell. These 2 outermost electrons are lost in the first and second ionization steps. But the third electron, the third outermost electron, is in the 2p subshell. And there's a big energy difference between 3s and 2p subshell. But now, let's have a look at vanadium. You can see from the first and second ionization energies, it's not much of a difference, right? It's almost like 700-ish difference. Then from 1370 towards 2870, it's again not much of a difference. Not 1400, rather 1500, but again, you know the idea. Why no big jumps? Why no big differences over here? because the ionization energies increase steadily, and you can notice that the overall difference between 4s and 3d subshell is not huge. For example, even for chromium, the ionization energies increase steadily. There's no major drastic differences. So ionization energy values show steady increase. It's not steep increase. The reason for this is that the energy levels of 4s and 3d are similar. Let me write that and show you. 1s2, 2s2, 2p6, 3s2, 3p6, and then let's say I'm considering 4s having 2 electrons and 3d having, let's suppose for example, 2 electrons in it. Or let's say 3 electrons in it. I know why I didn't write 2. For example, so the energy difference between 4s subshell and the 3d subshell is not big. Not big difference between 4s and 3d. So once the electrons from 4s are lost or 3d, they can both happen at the same time. So electrons from both orbitals, both subshells can be used in bonding. They both can be lost because again you can talk about the energy difference being not very big. I hope this is clear because they often ask this in P4 and we need to be able to be very explicit while we say that. So 4s and 3d subshells have similar energy, similar, not same. I hope variable oxidation state understanding is clear for us. Now let's talk about some typical differences between transition elements and group 1 and group 2 metals. So I'm going to talk about some properties. We're going to see how group 1 and 2 behave. We're going to see how transition behaves, and then we'll write an explanation for it. This will help you make your notes for P4 examination. So let's talk about density first. Group 1 and group 2 have lower densities. Transition elements have higher densities. The explanation is very simple, that the transition metal, basically their transition metal atomic radii is smaller. The radii are smaller basically, and their relative atomic masses are higher. So there is more mass clustered, present, or accumulated in smaller spaces. So more mass is present per unit volume as compared to group 1 and 2. So more volume as atoms occupy smaller volume. Another property is their melting/boiling point. So group 1 and group 2 have lower melting and boiling, but transition ones have very high melting and boiling. In order to explain this, we will take use of the concept of transition metallic bonding, transition metallic lattice. We'll say that they have stronger electrostatic attractions, and then we'll say their stronger electrostatic attraction is present because of more mobility of electron and higher number of protons. So between mobility of electrons and nuclei of cations, they have catalytic properties, another thing to talk about. But first let's talk about variable oxidation states. We have already talked about this, that group 1 and 2 have no variable oxidation states, but transition elements do show some variable oxidation states. The reason is very simple, that 4s and 3d subshells have similar energy levels, and electrons from both can be used in bonding. So ionization values increase steadily. This is also something we have already talked about. Steadily. So the electrons or number of electrons lost is variable. You don't also have to talk about electrons lost. It's also okay to talk about involved in bonding. The last property that I want to talk about here is the catalytic properties. They show catalysis. Group 1 and group 2 do not show, but transition elements do show that. The reason comes down to something of their d orbitals. For example, iron shows properties in Haber process, vanadium shows in contact process. Palladium and platinum are involved in catalytic converters. So the reason comes down to d orbitals being vacant. That allows, we have already talked about this concept before, but let's talk about it again, that d orbital allows the heterogeneous catalysis, but we will talk about it later again once we are done with the concept of complex formation. So I should write here to be continued. I hope these ideas are clear for you. In the next video, we'll talk more on them. Stay tuned.